Math is about finding patterns, such as the patterns of the sides for a right triangle. Then, if we find an answer, like the pattern revealed in the Pythagorean theorem, it doesn't seem that interesting because the pattern has been reduced to a formula. In this video, we will consider patterns from squares that may uncover something special, at least it was for me. We will think about this, hopefully special something, in three parts. First, we will review different perspectives of what the problem actually is. Then, we will walk through the solution, and we finish by uncovering the story behind this problem. And honestly, it's this third part that motivated me to create this video, so I hope you make it to the finish, even if I go off the deep end a bit. Okay, our story starts with this simple function that reminds us of algebra. You likely have seen its graph. The function doesn't change much if we double the output, which changes the function to y equals 2x squared. If we view the graphs side by side, they look similar. One thing that makes them look similar is they're both continuous. If we focus only on the positive real numbers as input, not only is the input smooth that we don't miss a number, but so is the output as we view the output of both graphs. We can imagine choosing any number as an output, say 8.82, and we know there is some input x value that will produce this output for both functions. Obviously, it will be a different x value, but it exists. But we can also think of this using geometry. So let's build 8.82 by thinking of it as an area. One equation was y equals x squared. And if x represents the length of a square, then y represents the area. And I'm using this yellow square to represent this expression. I'm defining the area to be 8.82, and we know there is some length, and we'll define that as x1, that produces this area. Then we can also get 8.82 by using two identical squares. That means the area for this green square is half 8.82, or 4.41. And I define the signed length as x2. And if you know your math facts, you may know that 2.1 squared equals 4.41, so 2.1 is the length of each side. And here's our second identical square. So visualize the area for the yellow square to equal the sum of the two green squares. The solution for the side of the yellow square isn't as clean of a result, but we know from the graph that the number exists because of the continuous flow. Okay, we can put the graphical and geometric perspectives together with this animation. Notice we equate the output for both expressions, the area. So the animation essentially illustrates the different side lengths that produce the same area. And as we expect, there is a solution for x1 and x2 for all these real number areas. With that idea in mind, think about this setup where the area for two identical squares equals the area for one larger square. We're not interested in this specific case, but more generally. So I will flip these squares over and we can think of this just in terms of the x1 and x2. We can write this as an algebraic expression where we want to find the solutions to this equation, where x1 is the length for the larger square and then x2 is the length for each of the smaller squares. Notice if we align the two smaller green squares next to each other, we create a rectangle. So this is also an exercise in engineering a square that has the same area as a rectangle, where this special rectangle has a width twice its height. Okay, a quick historical side note is that this is an offshoot from an old Greek math story that uses a quadrature concept. The idea is to take a shape, such as a rectangle or triangle, and create a square that has the same area as the original shape. We are playing a similar game today, but we're not limiting ourselves to using a compass and straight edge like the mighty Greeks. But let's add a different catch to make today's problem more interesting. Our catch is that we require both x1 and x2 to be an integer. That means we're restricting the lengths of the yellow and the green sides to be an integer. So our goal by the end of this video is we will answer how many sets of positive integer pairs x1 and x2 exist where 2x2 squared equals x1 squared. It was easy to find solutions when the input x's are real numbers because there are an infinite number of solutions. But if we limit input to integers, the problem becomes more difficult because we lose the continuous aspect to the graph. Now is a good time to pause and ideate how you would even begin to solve this problem, knowing there are an infinite number of possible x1 and x2 pairs. Perhaps one way to start is an example. Let x2 equals 5, then x2 squared is 25, and 2 of these squares becomes 50. So the larger square must have area 50. If x1 equals 7, the larger square's area is 49, which is 1 short. So we are close to a solution, but on the other hand, there is not a prize for being close. Here are the results for the first 10 integers. And notice none of the first 10 integers offer a solution. There would be nothing wrong with using a spreadsheet to try, let's say, the first 10,000 numbers to quickly identify solutions. And some of my colleagues actually try this approach. But if that doesn't produce a pattern to follow for all integers, there's not much benefit to answering our bigger question of all positive integers. Sometimes, though, finding one solution does give us insight into a more general answer, but let's bypass the sampling method and think of something else that can scale. Yes, scaling is the problem because of the sheer size of the positive integers. To me, this feels like David versus Goliath or some other similar story where the problem is too large. But David found a weakness in Goliath, so we must find the weakness in the infinite set of positive integers. So what is the weakness of the positive integers? Well, we can find the weakness by returning to our graph. The y values increase rapidly as x increases left to right on the axis. But we are only considering positive integer values of x because a distance must be positive. But traveling right to left on the x-axis, we find a beginning. And this means that the smallest possible value of x is 1. Knowing that there is a beginning to the positive integers gives us a clue. No matter how many solutions we uncover, there must be a smallest solution. There may not be a largest solution because there may be an infinite number of solutions. But since we know that there must be a smallest solution, let's consider this setup as the smallest of the set. If we use a building analogy, then the smallest solution is the first floor. Now, we do not know how many floors are above the first floor, but we know that there are no floors below the first floor. When we're thinking about a single solution, a geometric perspective often works best. And this is because it is specific and visual, which can highlight patterns. If we're thinking about this geometrically, one thing we have going for us is we have equal area. So let's visualize the 2 green squares and yellow square occupying the same area. We can start with the 2 green squares and put them side by side to create a rectangle. But if we put the larger yellow square on top, it always overhangs and we don't have much symmetry, so that doesn't seem to help. If we start with the larger yellow square, we can fit both green squares inside. To preserve symmetry, consider putting one square flush to the top left corner of the yellow square and the other green square flush with the bottom right corner of the yellow square. And since all shapes are squares, everything fits snugly together with no gaps. Yes, we still have overlap, but the overlap is within the bottom yellow square, so everything is contained and symmetrical, which is a good goal to pursue. Notice what happened with this setup. We've created new shapes. So let's think about these shapes and always remember the symmetry that we preserved in our setup. It requires jumping into some weeds to address some of the finer details, but I am sure you can handle it. Notice that there are two identical shapes in the bottom left and top right corners. These shapes appear to be squares, and they are part of the original large square, but not covered by the area of either of the two smaller squares. These shapes are yellow because they're not covered by the green squares. So let's refer to these shapes as the not covered region, since our goal was to cover the yellow with the green. We can identify the length of the two sides of each not covered region that form the yellow corner square as the difference between the length of the larger yellow square and the smaller green square, which is x1 minus x2. So, two lengths of the not covered region are x1 minus x2. We also know from symmetry that all four angles are right angles, so this is enough information to conclude that both shapes are squares, which means all four sides have length x1 minus x2. So I will refer to both these squares as the not covered squares. Okay, next observe that the shape in the center appears to be another square, which I will refer to as the double covered region since it is covered by the two green squares twice. And again, notice that the top left and bottom right corners form right angles since they are part of the green squares. And then by symmetry, all four angles are right angles, yielding the insight that the middle shape is either a square or a rectangle. Let's focus on the line that's extending from the center shape, which represents the side length of the smaller square. We've calculated the extended part as x1 minus x2, so we can deduce that the shape has a length x2 minus the quantity x1 minus x2, which we can simplify. This reasoning applies to all four sides of the shape from symmetry, proving that the shape is indeed a square, which I will label as the double covered square. And the last two shapes are not squares, but rather L-type shapes that are flipped, and these shapes are part of the original two squares that are not overlapped. They represent the single covered or covered once area that is not part of the other regions. Okay, this next step is a fun one because I've shown this problem to friends from a wide range of backgrounds, and usually those that have the least amount of math knowledge identify the next step the fastest and without help. So observe this picture, and what do you see? Let's repeat our inventory of the shapes we created. One square, the double covered square, two identical squares, the not covered squares, and two shapes like an L. If we only focus on the squares we created, perhaps there is a connection to the squares we started with. Notice both sets have one larger square and two smaller squares. The one double covered square in the middle can pair with the large square with side x1, and then the two not covered smaller squares on the corners can pair with the two squares with sides x2. And by our square setup, we reproduce our original shapes. An interesting concept if we think about it. And our curiosity may kick us in the direction to determine if there are more connections between this new set of squares and our original set. The key principle in the original set is equal area between sets. So let's take that thought and run with it to see if it is true. That means our next goal is to determine if the area for the double covered square equals the area for the two not covered squares. We can answer this question using basic algebra, which is where most math people gravitate to. Ironically, and again, my experience is those with less math background tend to consider a common sense approach, which is much faster and equally clever. Okay, first take a moment and compare these shapes on your screen, and I want you to first think of it in 2D. Do you have any conclusions? Even though our problem is about area, which is 2D, let's move to 3D because the extra dimension highlights the double covered and not covered concepts better. Since the total area of the green and yellow are the same by definition, I should be able to take a jigsaw and cut the green squares in a way that perfectly covers the yellow square. That's another way to think of equal areas, right? In other words, Green covers yellow once and only once. Okay, how do we do that? The L shapes are fine because they cover once. Check. Then the square in the middle is covered twice, but we only want it once, so assume I take a jigsaw and cut out one copy of the middle square, but leave one copy in place. Notice the two square corners are not covered. Once I remove one copy of the middle square, I should be able to cut it into pieces and cover the remaining yellow part, which is the final two squares. This must work because they have equal area, so green area and yellow area are the same in total. But what does that tell us? That tells us that this second copy of the middle square must have the exact same area as the area it is covering, which is the sum of the two smaller squares. That means the area for the middle square must equal the sum of the area for the outer two squares. Do you see it? Let's return to the rectangle in case you don't, or just to try to flex this muscle. Imagine placing any two identical squares next to each other to form a rectangle. Clearly, the sum of the squared area and rectangle area are the same, so that forms our equal area. Then if we slide the right square to the left, then we create a double covered area and not covered area relative to the rectangle, and those two areas must be equal. The same principle applies in our setup, but the shapes have different arrangements. But if you think of puzzle pieces, the double covered part must equal the not covered part regardless of shape. Let's pause and appreciate what we just did. We equated two very different areas without any math. Talk about something so simple yet powerful. But for those calculation-friendly folks, let's crank through the algebra. We've already identified the length of each square, so we can calculate the area of the not covered square by squaring the length of its side, multiplied by 2 to get its total area. And likewise, we get the area of the double covered square by squaring the length of its sides. Now compare the two areas and hope they equate. At first, it appears they do not equate because the expressions are different. But pause a moment and think about this. We should not expect those two expressions to be exactly the same. This is because this expression is not true for all x1 and x2 side lengths. It is only true if we assume we have equal area. So we should expect to invoke the equal area assumption somewhere along the way, and that somewhere is now. Notice the 4x2 squared represents the area for 4 green squares. We only need 2 on the other side. Also, we are 1 short of the x1 squared, which represents the area for the yellow square. Since we have our equal area assumption, exchange 2 green for 1 yellow in the equation, and then everything matches perfectly. Isn't it rewarding when you know what you want algebra to deliver, and it delivers exactly what you want? Yes, algebra and geometry tell the same tale. Are we allowed to say Eureka yet? It was insightful to reproduce our original setup, only smaller. Only smaller. Wait, recall we assumed that was the original setup was the smallest possible solution. But here we just created another setup, same as the original setup, only smaller. So we must have violated our original assumption that we had created the smaller solution because we created a smaller setup. Or did we? Is there something we have not yet proved? Recall in our original setup, we required both x1 and x2 to be integers. So if the lengths of the new squares are not an integer length, we did not break our assumption. Thus, our next ambition is to determine if the lengths of the sides are both integers. Fortunately, this answer is right around the corner. Recall we identified the not covered square length as x1 minus x2, and the length of the double covered square is 2x2 minus x1. Since both x1 and x2 are integers, both these lengths must be integers. Thus, we are now 100% confident that the lengths of the sides of the new squares are also integers, which allows us to conclude we successfully reproduce our original setup, which also means we are officially rule breakers and we violated our assumption that we had created the smallest setup. Okay, we broke a rule. Is there any harm or consequence from breaking our assumption? Certainly, we don't experience physical harm, but the consequence is that we know that there is no smallest solution. That may seem like a huge jump, but we jumped safely because we assumed our setup is the smallest solution. If we can identify that at least one solution exists, then there should be one solution which contains the smallest integer values. However, we just proved that the smallest solution cannot exist because there will always be one smaller solution. Therefore, there are not any solutions. And using our previous analogy, we found a floor below the first floor, but the building of positive integers must have a first floor with no floors below. Wonderful. We solved the problem. Check. But is there more to this problem than a solution? Is there an interesting story whispering in our ear? First, let me ask, is this the answer you expected, or were you surprised? Let's be honest, it is pretty remarkable we determined there are no solutions even though there are an infinite number of possible solutions. I think that idea is worth mulling over. But I also think that it is cool that we arrived at this conclusion simply by viewing a picture of squares. No calculator needed. Reminds me of one of my favorite phrases, no assembly required. Okay, that was remarkable, but does this story have any meaning or purpose in our mega math world? This problem seems obscure and trivial. Let's recycle our basic definition and do some simple algebra to modify our view. Although this is a valid equation when we input real numbers, we determined it does not work if we restrict x1 and x2 to be integers. With integer inputs, then we must replace the equal signs with an unequal sign. In other words, we write this as an inequality when we restrict our domain to positive integers. Next, rearrange by dividing both sides by x2 squared. We can do this for inequalities just like equations. Taking the square root of both sides yields this inequality where root 2 is the positive square root of 2. Okay, our equation is recycled, but does this new perspective mean anything? Remember, the definition for a rational number is that we can write it as the ratio of two integers. Notice what we're saying here is that we cannot write root 2 as a ratio x1 divided by x2. Since x1 and x2 are both integers, this means we cannot write root 2 as a ratio of two integers. And that, my math colleague, tells us that root 2 must be irrational. We can make that claim because if root 2 was rational, then it would have integer solutions for x1 and x2, and we just proved that they do not exist. Yes, this is more than a problem about squares. It is a story about proving root 2 is irrational. We also get a sense of root 2 in the story by assuming the length of the small square, x2 equals 1, the smallest possible integer. For this case, we can solve for x1, the length of the longest square, but also the squares within the squares. We know there are no possible integer solutions, but it is interesting to view the solution when we use the smallest integer and then observe all the other lengths are functions of root 2. Okay, now that we know root 2 is the focus of the story, pause the video and relook at our square setup and ask yourself, do you see the proof from beginning to end? Can you visualize how we know root 2 is irrational? This is the ultimate goal for this video, is that you see the entire story in one simple picture. Okay, that's the end of the story, so you can rest your math brain. But the part I get most excited about is thinking about what happens if we actually measure root 2 as a physical distance, like an ant or even smaller crawling on a ruler. This may seem weird, but hey, play with me here. First, we know this distance exists, right? So if this square here is length 1, and I create a diagonal, then by the Pythagorean theorem, the length is root 2. But if I want to quantify it or measure this distance with a ruler, crazy things happen. Sure, we know it's between 1.4 and 1.5. However, that only divides a ruler into tenths, or 1 decimal precision. We likely own one of those rulers. So let's fine-tune our precision to these two numbers with more than 60-digit precision. We know the length of our hypotenuse is in between these two numbers because we know that when we square each, we straddle 2 in the result. Root 2 is a nice irrational number because we can easily confirm whether a number is exactly root 2 by squaring itself, assuming we have the math power to do so. Okay, leaping further, here are the first 5,000 digits of root 2. This is closer to the correct measurement, but still not exact. We get even closer to this correct distance by using a number with 10 trillion digits of precision. Yes, 10 trillion. And yes, we geek humans know this number. We also know it is much closer to the true length of this diagonal, yet it is still not exact. This is not just geeky, it is impressive. This number is so long that if we spoke 1 digit per second, it would require more than 316,880 years to speak. And we can increase our insanity and assume there was this crazy minute insect that took steps on a number line where the distance of each step is exactly the Planck constant. This is the smallest distance in the universe that has a physical meaning. Yet, even with these incredibly small steps, as this insect would walk on the number line, it would not step on the real root 2, but cross over it. If it was walking the diagonal, it would not end on the diagonal, but walk over it. Do we know root 2's value to this precision? No, not even close. But we do know is that root 2 is infinitely precise. We know this without even knowing this number. And we know this how? We know this from our simple story of squares. And how confident are we that this is true? We are 100% confident. Take a moment and let that sink in. There is a hidden infinity lurking in a simple square. Okay, back to Earth. We can agree that the square root of 2 is on our calculator, so it is part of this world. But clearly, this is the rational version, the one rounded to only a few decimal places. It is not the real root 2. The root 2 we are talking about is the irrational version, the one that is not of this world. Irrational root 2 is not of this world because it is infinite and we cannot define it with numbers because we are finite. So, what world are we entering into when we do this kind of math, where there is infinite precision? Not only what world is this infinite world, but what allows us humans to enter into this world. Sure, a square is defined by 4 equal sides and 4 right angles, and appears simple enough. That is what most people see. But perhaps you see something remarkable hiding within a square once we take a shortcut between 2 points and cross the diagonal. As I think of its simple design, yet containing an infinite mystery hiding in the diagonal, I ask myself, who is the one that engineered the squared? And what must their mind be like? Well, thanks for hanging with me. I know this was long, but it is only the beginning of this story, as there are many branches from this topic. One branch that is more of an extension of this branch is to prove root 3 and root 5 are both irrational. And here are a couple of pictures to get you started. It is neat to extend the idea that we used in this video with squares and see it reappear with other basic shapes, such as regular triangles and pentagons. What can you say? Math takes the most simple things as input and generates mind-blowing ideas as output. There are so many ideas that branch from today's story because today's story is part of the big beginning of proofs in math. But the downside to the Greeks' thinking is that it stifled ideas about algebra for about 2,000 years. And the real numbers were not officially defined until 1879, even though we knew about the irrational numbers from the Greeks. Talk about a time gap. Well, I'll be providing more content on these subjects as my time allows. But I'll leave you with one more thought. Let's take a look at these squares one more time. We'll start with the two green squares, put them together side by side, forming a rectangle. And let's just flip the side over and we will create this shape. And let's move it over here so we have some space. Now what we have is our final yellow square, thinking, does this fit in the picture anywhere? Well, let's just take this guy and move him over here and see how it fits between those two corners. And boy, it just appears that thing fits snugly. Well, the reason why that occurs is a question for you to answer. And if you think like a Greek, then you will identify your own eureka moment.